Record cold grips the northern plains. That winter, ranch surveys and later histories estimate that hundreds of thousands of cattle die in the open, many within sight of unfenced line camps and log bunkhouses. The United States Signal Service maps for the region show repeated intrusions of Arctic air, driving night temperatures into the -30s and -40s from Montana into Wyoming. Inside most cabins, the failure point is not the stove, but the seams, gaps between 8 to 10-inch logs packed with stones and split billets, skimmed with clay or cement, and now cracked from a season of shrinkage and freeze-thaw. Yet in some timbered basins, builders begin substituting sawdust, waste from nearby mills, as the bulk of their daub. Light, fibrous, bound with lime and clay, sometimes salted. These seams flex instead of shattering. In a winter that ends the open range, the math between wood wasted up the flue and wood buried in the walls will decide who winters in place and who leaves. Frost feathers form along interior log seams, while the center of the wall stays bare. The pattern appears in cabins from the Missouri breaks to the Yellowstone valleys. Homesteaders wake to find ice skims on water buckets 3 feet from the stove. They assumed 8 to 10-inch softwood logs with traditional chinking and daubing would provide adequate shelter through average winters. The 1880 to 1881 hard winter, documented in meteorological studies and local accounts, exposes how marginal many single-pen cabins really are. The United States Signal Service and Army Post observers keep daily temperature and snowfall records. Their logs show weeks where mercury never climbs above 0 Fahrenheit. Blizzards arrive in October instead of November. Snow piles deeper than eaves. Winds scour the plains at 30 to 40 miles per hour for days without pause. Typical homestead walls stand 7 to 9 feet high. Footprints measure 14 by 16 to 16 by 20 feet. Logs are 8 to 10 inches in diameter, round or hewn, joined at corners with saddle or V-notches. Between the logs runs a 3-part system: rigid blocking made from stones and short billets, soft filler of moss or dry clay or dung, and an outer mortar of clay, lime, and sand. Preservation briefs from the National Park Service describe chinking as whatever is most conveniently at hand, but warn that poor maintenance leads to drafts and decay. The system works if logs are seasoned, if chinking stays intact, if winters stay moderate. Green logs shrink 1/4 to 1/2 inch over the first years. Outer skins check. Hairline cracks open along log edges. Each crack becomes an air jet in -20-degree wind. Fuel consumption doubles. Inside surfaces frost over even with the fire roaring. Most cabins met the letter of the homestead law. Few were engineered for a winter that never let the seams rest. A hardware clerk opens a freighted barrel of Portland cement stamped with an Ohio mill brand. Gray dust hangs in the depot air as sacks are loaded for the interior. Advertisements and trade notices present Portland cement and wire mesh as permanent upgrades to old-fashioned mud daubing. Freight costs are high. A 300-pound barrel costs more than 50 pounds of lime and must be hauled by wagon from the railhead. Storekeepers order them anyway. Builders believe the investment will pay off. Over the next decades, conservation reports will document how those rigid systems often accelerate decay in log walls. Typical retrofits follow a standard pattern. Workers tack wire mesh across gaps. They trowel cement-rich mortar 1 to 2 inches thick over existing filler. The work looks solid. The seams appear permanent. The National Park Service and restoration guides now caution against high cement daub and mechanical fasteners. They note patterns of cracking, trapped moisture, and stained, rotting logs. The physics are straightforward. Cement has low tensile strength and low flexibility. It follows the log only until the first full seasonal cycle. After that, every expansion and contraction rights cracks along the interface. Daily temperature swings of 30 to 40 degrees Fahrenheit are common in shoulder seasons. Winter brings repeated freeze-thaw cycles. Logs expand when wet, contract when dry. Cement cannot accommodate this movement. Hairline cracks appear, water enters, freeze-thaw widens the cracks. The bond fails. Where cement debonds, it creates a pocket behind the rigid shell. Moisture accumulates, rot begins. The very durability that made cement attractive, its hardness, becomes the problem. A brittle seam cannot heal itself. A flexible one can. The more modern the seam, the faster some cabins began to fail. A waste pile of sawdust and shavings rises higher than a freight wagon, smoldering at the edges in summer heat. Millmen see sawdust as a disposal problem. It accumulates faster than they can burn it. Some mills dump loads into creeks. Others let piles smolder for weeks, releasing acrid smoke. The material has minimal value, used for bedding in stables, packed around ice houses, stuffed into attic spaces for insulation. Builders usually see it the same way. Loose fill, packing material, not structural. Yet by the early 20th century, analyses of historic daub show wood fiber as a common component in some regions. Conservation reports document lime, clay, sand, and wood pulp or fiber mixed together as deliberate mortar. Not loose sawdust stuffed into gaps, but sawdust bound with mineral binders to create a cohesive mass. Builders influenced by traditions that already used hair, straw, and other fibers in mortars and plasters make the leap. If animal hair reinforces clay, why not wood fiber? If straw distributes stress in plaster, why not sawdust in daub? Daily mill output might reach 5,000 board feet. The ratio of lumber to waste runs roughly 2:1 by volume. For every wagon of lumber leaving the yard, half a wagon of sawdust piles up. The material is dry, relatively clean, and free. Known practices of filling double walls or attics with sawdust in 19th and early 20th century buildings demonstrate awareness of its insulating value. The step from loose fill to bound aggregate is small in theory, but significant in practice. When fibers enter the mortar instead of sitting loose in cavities, they change shrinkage behavior and crack patterns fundamentally. What mills burned or dumped by the ton would later show up in the seams that survived. A framing square and rule lean against a newly raised 16 by 20 foot single-pen cabin, notches still bright from the axe. The visible gap between two log rounds ranges from less than an inch to nearly 4. At the notches, where logs rest on one another, the fit is tight. At mid-span, where logs curve away from each other, the gap opens. A carpenter's hand fits easily into some sections. Many cabin guides focus on notch types and roof pitch. Few treat the long-term behavior of the gaps between logs. Conservation and engineering analysis treat those joints as a structural system in their own right. A typical 16 by 20 foot cabin has roughly 120 linear feet of seam per wall course. 8 courses yield nearly 1,000 linear feet of joints requiring chinking and daubing. If the average gap is 2 inches wide and 3 inches deep, that represents over 40 cubic feet of material just to fill the voids, not counting the outer skin. Shrinkage ranges for green softwood logs run from 1/4 to 1/2 inch in diameter over 2 to 3 years. Daily temperature swings of 30 to 40 degrees Fahrenheit in shoulder seasons drive expansion and contraction. Each cycle is small, a few hundredths of an inch, but repeated thousands of times. Technical language from preservation briefs explains chinking and daubing as a 2-part or 3-part system whose maintenance is essential to the weather tightness of a log wall. When that system fails, infiltration spikes, heat loss accelerates, interior frost forms. Each rigid seam effectively tries to pin 2 moving members together. The mortar cracks, the bond fails, air leaks through. Flexible seams ride the movement, maintaining contact. In the long run, the smallest part of the wall did the most work. A lime pit bubbles quietly beside a creek. Sacks of clay, barrels of salt, and a heap of sawdust sit nearby under a rough shed. Traditional daub uses lime, clay, and sand, with fibers like straw or hair as binders. Substituting sawdust seems risky until laboratory and field analyses show wood fiber-rich daub performing well over decades. The recipe families reconstructed from period and conservation sources suggest several parts sawdust or wood pulp to 1 part lime clay binder, plus modest salt. Ratios vary by site and available materials. Where clay is rich and sticky, less lime is needed. Where sawdust is coarse, more binder holds it together. Where fine shavings are available, the mix gains cohesion with less effort. Each component plays a specific role. Lime provides slow carbonation and long-term strength. It sets through reaction with atmospheric carbon dioxide, a process that takes months but produces durable results. Clay acts as an initial binder, giving the mix workability and early adhesion to wood and fiber. Sawdust serves as low-density, flexible aggregate. It distributes stress. It creates internal reinforcement as fibers interlock. Salt functions as a simple preservative and moisture moderator borrowed from timber and plaster practice. The mix is counterintuitive. Lime and clay are dense. Sawdust is light. Combined, the result weighs less than conventional sand-based mortar. Lower density means less shrinkage stress. Fiber content means microcracks dissipate through the matrix instead of opening single large failures. A 1939 Woodcraft description mentions wood pulp plaster with cement mortar. Modern guidance favors lime-based, fibered mixes over cement for historic log buildings, citing better flexibility and breathability. Shifting aggregate from sand to fiber changes the internal stress map of the seam. Instead of one big shrinkage crack, many micro-movements dissipate force. Once sawdust moved from the floor to the mix, the seam stopped fighting the logs and started following them. A long wooden trough is filled with a pale, fibrous slurry. A ranch hand tests it with the back of a trowel. The material holds a peak without slumping. Ribbons trail from the tool's edge. Builders often treat daub as a one-season patch job. Field practice and modern restoration show it needs careful batching and curing to last. Slaking quicklime in barrels days in advance creates putty. The process is exothermic. Water and lime react violently, generating heat and expanding the material. Once slaked, lime putty can sit for weeks or months, improving workability. Screening bank clay through improvised sieves removes stones and root fragments. Hauling sawdust from mill heaps in sacks and sleds brings the final ingredient to the worksite. The packing sequence follows a logical order. Workers rake out loose or failed daub from previous seasons. They insert dry blocking, stones, short billets, bark slabs, where gaps exceed roughly 3 inches. This saves mortar and reduces the span the daub must bridge. They pack sawdust mortar from both sides, inside and out, building in 1 to 1.5 inch lifts until the gap is full. They tool the outer face with a slight outward fall to shed water. Target consistency matters. Too wet and the mix slumps, creating voids. Too dry and it won't adhere. Ribbons off the trowel, holds a peak without slumping, translates to roughly 30 to 40% moisture by weight. Enough for workability, not so much that shrinkage cracks become inevitable. Restoration guides specify removal of loose and non-adhering daub, identification of original mixes, and recommendation of lime-based fibered replacements. Proper lift depth and moisture content prevent internal voids and shear planes. Good curing reduces long cracks to shallow surface checking. Extra time in the trough and at the wall meant fewer trips back with the trowel in midwinter. 3 simple mercury thermometers hang at eye height beside 3 different chink lines. Frost outlines tell their own story. On paper, a cement-rich seam appears superior. Under real freeze-thaw and log movement, a lighter fibered seam holds contact and cuts infiltration. Agricultural experiment stations and later building science efforts model heat loss and leakage. Ranch and homestead accounts document fuel use and comfort. The data allow comparison. Consider 3 wall assemblies under shared winter conditions. First, clay straw daub, traditional mix with modest lime content. Second, cement heavy mortar with wire mesh, the modern upgrade. Third, lime clay sawdust mortar, the fibered alternative. Use simplified R values and air change estimates. Assume exterior temperature of -20 degrees Fahrenheit, interior target of 60 degrees Fahrenheit, moderate wind. Model interior surface temperature near the seam and likely crack formation rate under repeated freeze-thaw cycles. Clay straw daub performs adequately if well maintained. Shrinkage creates shallow surface cracks. Adhesion to logs remains fair. Estimated air infiltration through hairline cracks adds roughly 20 to 30% to baseline heat loss. Cement-heavy mortar starts strong but degrades quickly. First freeze-thaw cycle opens microcracks at the log interface. Each subsequent cycle widens them. After 1 season, debonding is visible. Air infiltration rises to 40 to 50% above baseline. Interior surface temperature drops noticeably near failed seams. Lime clay sawdust mortar shows different behavior. Initial adhesion is good. Shrinkage is modest due to low-density aggregate and fiber reinforcement. Seasonal movement of logs is accommodated by slight compression and expansion of the fibrous matrix. After 1 season, surface checking is minor. Adhesion remains intact. Air infiltration stays below 15% above baseline. Cutting leakage by even 20 to 30% across all seams of a typical 16 by 20 foot cabin translates into several cords of wood saved per season. A seam that flexed a few millimeters could save several tons of wood. A conservator gently breaks away a loose outer patch to reveal older daub beneath, fibrous and still bonded. Later owners assume cement overlays are an improvement. Detailed conservation work often finds the opposite. The oldest, fiber-rich mixes are in the best condition. Historic American buildings, survey teams, museum staff, and log building specialists document construction layers. They take core samples from chink lines. The samples reveal stratigraphy, original lime clay fiber daub at the log interface, later cement-heavy overlays in the middle zone, sometimes modern synthetic products on the surface. Under magnification, early mixes show wood pulp or fiber, lime nodules, and fine aggregate. Fibers run in random orientations, creating a tangled mat. Lime crystals bridge between fibers. Clay particles fill voids. The structure is coherent but porous. Later layers are dense, brittle cement. Aggregate is sand or crushed stone. No fibers. High compressive strength but low tensile strength. The boundary between original daub and cement overlay often shows a clean separation. The rigid cement has debonded. Visual inspection supports the lab findings. Original mix is cracked but bonded to both log faces. Overlays have pulled away, creating voids behind. Moisture stains mark the wood. Rot has begun in some cases. Conservation reports note that cement-rich daub often has to be fully removed to prevent further damage. Surviving original mixes require only localized repair. The recommendation is clear. Remove the rigid overlay, retain the flexible base, patch with compatible lime fiber mortar. The physics are straightforward. Flexibility and permeability in the original seam allowed seasonal movement and drying. Rigid, vapor-tight overlays trapped moisture and cracked. The seam that could move with seasonal log changes remained adhered. The seam that tried to stay rigid debonded and admitted water and air. Where cement failed in decades, a light fibrous daub had already held for half a century. A survey sketch shows drifts over fence lines. Frozen carcasses pile against wire as chronicled in range reports. Fence posts vanish. Coulees fill with snow and dead stock. Open-range ranching assumes mild enough winters and mobile herds. Cattle can graze through moderate snow. They drift with storms, finding shelter in draws and creek bottoms. The 1886 to 1887 Big Die-Up proves that model fails when conditions exceed historical norms. Ranchers whose letters and later interviews describe losses of 50 to 90% of their cattle leave a stark record. Weather observers document repeated blizzards and record lows. Storms arrive in November and continue through March. Temperatures plunge to negative 40 degrees Fahrenheit. Snow piles 4 to 6 feet deep on the level, deeper in drifts. Many outfits operate with minimal fixed shelter. Light sheds, thin-walled bunkhouses, line camps with single-thickness log walls, and minimal chinking. When temperatures drop and stay down for weeks, these structures become barely habitable. Typical ranch structures vary widely. Some have substantial log barns and well-sealed line camps with 8 to 10-inch walls, decent roofs, tight doors. Others make do with rough sheds, 6-inch poles, bark roofs, and gaps you can see daylight through. Fuel logistics become critical. Timber must be hauled from distant stands once nearby wood is exhausted. A poorly sealed cabin might burn 6 to 8 cords per month in extreme cold. A tight cabin might use 3 to 4 cords. The difference is not just comfort, but survival. Hauling capacity per sled or wagon is limited. Deep snow makes trips dangerous. Running out of wood in mid-January means death. Where wind-tight walls and roof lines exist, stock and men can ride out more of the cold. Where they do not, losses are absolute. In many counties, the difference between a cabin and a box with gaps showed up in the spring tax rolls. A log wall bears charcoal marks where each rank of firewood was stacked and burned through the winter. By spring, not all of them are gone. Many settlers treat firewood as labor, not as a design variable. When winters like 1886 to 1887 arrive, the cost of poorly sealed cabins becomes clear in both time and risk. Agricultural reports and farm bulletins summarize average fuel use in cold regions. Later building science reconstructions tie air leakage to extra cords burned. The numbers allow a worked example. Consider a 16 by 20 foot log cabin. Wall area totals roughly 700 square feet. Seam length runs approximately 1,000 linear feet across all courses. Average gap width is 2 inches, depth 3 inches. Estimated air infiltration through poorly sealed or failed daub might add 30% to baseline heat loss. If effective sawdust mortar reduces that infiltration by 20 to 30%, cutting it nearly in half, the fuel savings become quantifiable. Translate saved BTUs into cords of wood. At elevation, in snow, 1 cord represents 8 to 10 hours of cutting, hauling, and splitting. A cabin saving 3 cords over a winter saves 24 to 30 hours of heavy labor. That labor occurs in the coldest, most dangerous part of the year. Frostbite is common. Falls are frequent. Exhaustion is inevitable. Avoiding even a week of extra wood trips reduces injury risk and preserves energy for other critical tasks. Period articles urge better house insulation and tighter seams in cold climates, even before central heating becomes standard. The advice is grounded in fuel economy and safety, not comfort alone. Each cord saved is not abstract. It is time. It is reduced exposure. It is margin when conditions go bad. 3 inches of waste in the seams could spare several weeks of work at the woodpile. A restorer taps a cement band with a hammer. It rings, then fractures away from the log in a single shell. Behind it, a hollow space. The original daub is gone. The log face is stained. Rot has begun. Mesh and cement systems had been sold as upgrades. Restorers in the early 20th century begin documenting how often those systems fail and damage logs compared to traditional woodblock chinking and lime-based daub. Craftsmen quoted in trade and regional history pieces describe chink, daub, repeat methods. They prefer breathable, flexible mixes. They note that rigid systems trap moisture and accelerate decay. Failure modes follow predictable patterns. Mesh rusts where moisture accumulates. Cement cracks along the log interface. Water follows the cracks, penetrating behind the rigid shell. The log face stays wet. Staining appears. Fungal growth begins. Wood fibers soften. Rot spreads. Comparative lifespans show the problem clearly. Cement bands last 10 to 20 years before major failure. Original or fiber-rich daub, if maintained, can last 50 years or more. The permanent solution fails faster than the primitive one. Articles and guides explicitly warn against cement. They advocate for lime clay with indigenous aggregates as healthier for the structure. The language shifts from strength to compatibility. The goal is not maximum hardness, but matched flexibility. Recognition that rigid, non-breathing systems shorten log life shifts conservation practice. Modern restorers are trained to remove cement carefully, inspect underlying logs for damage, and re-chink with materials that match original properties. Lime-based binders, low-density aggregates, fiber reinforcement. The same physics that governed frontier cabins, moving logs, freeze-thaw, moisture paths, forced 20th century restorers back toward the material logic of flexible, fiber-rich, breathable seams. What had once been sold as progress was now something restorers were paid to remove. A slide projector throws an image of a 19th century cabin seam. Pale, fibrous, intact after decades of weather. The audience leans forward. For decades, fibered sawdust mortars are treated as local quirks, mountain tricks, improvisation born from scarcity. As more cabins are documented, they come to be seen as early, effective solutions to a general problem. Sealing moving timber walls. Preservation architects compile regional guides to historic log construction. Log home builders seek durable, historically compatible chinking methods. The principles distill into simple statements. Moving timber walls require soft, sacrificial joints. The seam must accommodate seasonal expansion and contraction without losing adhesion. Rigid materials cannot do this. Flexible materials can. Local waste, sawdust, shavings, plant fiber can be structural when bound with modest mineral content. The aggregate does not have to be expensive or imported. Scrap materials work if the binder ratio is correct. Seams must remain permeable enough for slow drying. Trapped moisture causes rot. Breathable mortars allow vapor to escape. Vapor-tight barriers trap condensation. These principles echo in later practices. Cordwood masonry uses sawdust insulation between inner and outer walls. Wood fiber insulating boards become common in mid-century construction. Modern synthetic chinking products are marketed on flexibility and adhesion rather than strength alone. Conservation manuals treat lime and compatible. Aggregates, not cement, as the standard for historic log structures. The shift is complete. What frontier crews improvised for survival becomes codified as best practice because it obeys the physics of timber and climate better than many advanced materials. What started as mill waste became a design rule. Seams should move at least as much as the walls they seal. A conservator lays 3 small bags on a table, each labeled clay straw daub, cement, sawdust lime clay mortar. Beside them, a notebook of field observations, lab results, maintenance records. Modern testing and a century of field evidence allow a final comparison. The fiber-rich, sawdust-based daub consistently shows better adhesion, crack control, and moisture behavior on historic logs than cement-rich alternatives. Scientists and craftsmen jointly recommend compatible, flexible materials in preservation briefs and technical notes. The guidance is specific. Use lime-based binders. Favor low-density, fibrous aggregates. Avoid rigid, vapor-tight systems. Side-by-side lab metrics confirm field observations. Compressive strength. Cement is higher, but irrelevant. Chinking does not bear loads. Tensile strength. Fiber-rich daub is superior due to fiber bridging. Vapor permeability. Sawdust mortar allows drying. Cement blocks it. Shrinkage. Sawdust Mortar shrinks less and cracks smaller. Adhesion, flexible mortars maintain bond through seasonal movement. Rigid mortars debond. Approximate maintenance intervals over 50 to 100 years show the long-term picture. Cement-rich daub requires major repair or replacement every 10 to 20 years. Fiber-rich daub needs only minor patching every 20 to 30 years if properly maintained. A simple ledger-style comparison makes the economics clear. Cost per cubic foot, cement daub runs higher due to material cost and freight. Lime clay sawdust runs lower. Sawdust is free, lime and clay are cheap. Estimated cords of wood saved per season. Tight cabins save 2 to 4 cords compared to leaking cabins. Over a decade, that compounds to 30 to 40 cords. Freight loads saved by using lighter mixes reduce wagon days and transport costs. The long view confirms what field improvisation suggested. In a climate of moving logs and killing cold, flexible, scrap-based seams outperform rigid, expensive ones. In the surviving walls of the American West, 3 ingredients from the scrap pile, lime, clay, and sawdust, quietly outperformed the proudest barrels of cement. If you value fact-grounded frontier engineering and the small, tested tricks that kept people alive, consider supporting the channel.